Okay, so now we are going to look at the fundamental theorem of arithmetic. So this is Theorem 131. So the specific statement is this: any a greater than 1 can be factored in a unique way as a is equal to p1 to the power alpha 1 times p2 to the power alpha 2, like that it goes till pn to the power alpha n, where p1 is strictly greater than p2, p2 is strictly greater than p3, like that the smallest one is pn, and these are prime numbers. And alpha 1, alpha 2, etc. up to alpha n, these are positive integers. Okay, so this is the statement of the theorem. So essentially it is saying that if we have an integer, a positive integer greater than 1, then for that there will be finitely many distinct prime numbers pi and an equal number of positive integer exponents alpha I, such that a can be written like this. And this representation is unique, that is, for such a given a, there will be only one set of pi's and one set of alpha i's. So we are now going to prove this. So actually this theorem is actually two theorems at once. The first one states that for a given a, such a representation exists, and the second part states that this representation is unique. So we are going to prove each one of these parts separately by using inaction. But the version of induction that we will use is this one. So you already know this from the discussion we had about induction when we developed the system of natural numbers. But anyway, let's just again look at this. So it goes like this: if m0 is an integer, is a positive integer, I can restrict it to be positive, is any positive integer and Pn be any statement pertaining to the positive integer n, such that Pm0 is true and the truth of pk for all k satisfying these inequalities implies Pm is true. Then Pn is true for all n greater than or equal to m naught. This portion of the induction we are going to use. Okay, so this is the thing that we are going to use to prove the two parts. So I am not writing that this is the version of the induction we are going to use. You understand this. So I am not writing the proof exactly formally the way it is supposed to be written, but you get the idea. This is something. This is what we are going to use. So first of all, we are going to prove that every integer greater than 1 has one such representation. So that is the first part, existence of a factorization like this. Okay, so we will start induction, but note that now our m naught is 2, it's not 1, because a, the smallest value a can take is 2. So when a is equal to 2, or let me just first write this, otherwise it may be confusing. We first prove by induction that for any a greater than 1, there exist prime numbers p1 greater than p2, etc., greater than pn, and positive integers alpha 1, alpha 2, etc. to alpha n, such that a is equal to this. This is what we are going to prove. Note that this is not the entire statement, because we have left this out in a unique way. This part is the second part. So here we are going to prove only existence. So let us start the induction. If a is equal to 2, then obviously a has a representation of the said form. What this means is that if a is equal to 2, then a can be written like this. How? Specifically, what are the choices? In this case, n is equal to 1, so there is only p1, only one prime. p1 is equal to 2 and alpha 1 is equal to 1. So it's just this. This is representation when a is equal to 2. So for a equal to 2, the statement is true. Now assume any integer, we made the convention of not using the word integer, right? Now any, assume that any or to be more specific and not really somewhat vague, let me write like this. Now assume any k satisfying satisfying 2 less than or equal to k less than a has a representation of the state form. Okay, so this is our assumption, or this is our induction hypothesis. What have we assumed here? We have assumed that all the integers starting from 2 until we reach a, that is till a minus 1, each one of them has a representation of the state form. That is, any one of them can be written like this for some primes and for some positive exponents. Okay, so this is my induction hypothesis. Okay, now I have to say the same thing for a, right? Now, if a is itself prime, then obviously a has a representation of the state form. Why? You just look at this special case. Here a was a prime. So in much like how this is, in this case it's trivially true that a has a representation of the state form. If a happens to be any other prime, in that case also you can see that n will be 1, p1 will be a, and alpha 1 will be 1. Okay. So here again I am not writing those conditions. So this is one case. The other case is that a is not prime. If a itself is not prime, then being not prime means it has a non-trivial factorization. What that means is that a is equal to, you can write a as b times c for some integers b and c satisfying b and c satisfying Okay, how are these inequalities coming? It's because you see that since a is not prime, the factors b and c can be chosen in such a way that none of them is either 1 or a. That is, they are non-trivial factors, right? Only when p is a prime, the only possible factorizations are this: 1 times p or p times 1. So if this is your A, this is B and C, then B can either be 1 or P. Other factors, if it happens to be something else, then it will lie strictly between 1 and P. Each one of them. So in case of P, now we have A. So since it's not prime, so B strictly lies between 1 and A. So that means it's greater than 1 and less than A. And being greater than 1 means being greater than or equal to 2. Okay, so the smallest possible value is 2, the largest value is of course A minus 1. Okay, but now you look at this inequality and look at our induction hypothesis. It says that if we have an integer k satisfying these inequalities, then k can be represented as a product of primes, or in other words, k has the state representation. So because B and C are now satisfying these inequalities, each one of them will have a representation of the state form. That is, each one will be a product of some primes. But then their product will also be a product, such a product. So by the induction hypothesis, both B and C have representations of the state form. Hence, A equal to BC also has a representation of the state form. This completes the induction. Okay, so and it proves that any A greater than 1 has a representation like this as a product of powers of distinct primes. Now we come to the second part of the proof, which says that this representation is unique. Okay, next let us just state in a mathematically precise way what we mean by this uniqueness. Next, we show that if A is greater than 1 and there exist primes P1 greater than P2, etc. greater than, let me wrap this up. If there exist primes, this comma more, these are also primes, Q1 greater than Q2, which is greater than Q3, etc. up to Q say M, and positive integers alpha 1, alpha 2 up to alpha n, comma beta 1, beta 2 up to beta m, such that A is equal to P1 to the power alpha 1 times P2 to the power alpha 2 like this up to Pn to the power alpha n, which is also equal to q1 to the power beta 1 times q2 to the power beta 2, like this up to qm to the power beta m. Then if these things happen, then let me just wrap the statement up, since we already know, we have seen what it says. We need some space. Then the first claim is that n is equal to m. This is the first claim. The second claim is that the corresponding primes, corresponding means P1 corresponds to Q1, P2 corresponds to Q2, Pn corresponds to Qn, because if we prove the first claim, then the number of primes in each such representation becomes the same, and then they will correspond to the primes will come into a one-to-one correspondence. Now those corresponding primes are equal. That is the second claim. Pi is equal to Qi for I lying between 1 and n. Now after this claim, this makes sense. And the third one likewise is that the corresponding exponents are equal. Alpha I is equal to beta I for I lying between 1 and n. We have to specifically prove this. And for this, again, we are going to use induction on A. And what version of induction? The one we have used here in the first part. Okay. So here also, we use induction on A. Here also we will use induction on A. So the first value of A is naturally, since A is greater than 1, the first value is A is equal to 2. When A is equal to 2, the claims 1, 2 and 3 are obvious. Why? The thing is that if A is equal to 2, then one factorization is 2, just 2. If we have any other factorization, there we can prove that that factorization also has to be equal to 2. And this is, it may not be obvious to you, but if it is not obvious, I am putting an asterisk here. What this means is that either this is obvious to you, if not, then prove it. I leave it to you. Okay, so when A is 2, then 2 is the only prime factorization. So let us now move towards the induction hypothesis. Now assume that the claims 1, 2 and 3 are true for any k satisfying this. Okay, this. Okay, now let a greater than 1 have the representations a equal to p1 to the power alpha 1 etc. equal to q1 to the power beta 1, q2 to the power beta 2 etc. to qm to the power beta m, where the usual things, but for the sake of completeness let me just write them. P1 greater than P2 is greater than Pn, and Q1 greater than Q2 are primes, and these are positive integers. The spelling is wrong, no? Are positive integers. Assume. Yes, there will be an E. Okay, so positive integers. That's what I was thinking about. Anyway, so this is our situation. Now here we have to prove the claims 1, 2 and 3. Sorry, this is equal. Okay, so how do we go about proving this? From alpha 1 greater than 0, we see that P1 divides A equal to this. Okay, where is this condition coming from that alpha 1 is greater than 0? Here, from our hypothesis that these are all positive integers. So alpha 1 is greater than 0, which means that P1 appears as a factor in the factorization of A, actually appears. Okay, so A is P1 times some other integer. Actually, it looks like this, right? P1 times alpha 1 minus 1 times P2 to the power beta 2 etc. up to Pn to the power, no, this is not beta 2, this is alpha 2, alpha n, and this is an integer, so that means P1 divides A, but A is also equal to this, so P1 divides Q1 to the power beta 1, Q2 to the power beta 2 up to Qm to the power beta m. right? Okay. Now, by the corollary to, what was that corollary? So these things I can't remember, the numberings. Let me just see what corollary it was. The one which says that if a prime divides a product of some integers, then it divides one of them. Right, that thing. Do I have it here somewhere, or I will have to look at the previous parts? I just want the number, exercise. All the things have got jumbled. Then it must divide at least, yeah, this is the corollary. Corollary to lemma 132. Okay, so now here look at this. P1 is dividing a product of some primes, right? Where we can think of this as a product of primes in which some primes are getting repeated. Like Q1 will be repeated and there will be beta 1 number of Q1s, then times beta 2 number of Q2s. That does not matter. The corollary does not say that the factors should be distinct. Some of them may be equal. In fact, all of them may be equal also, if these things are not present. If m happens to be equal to 1, then we have only Q1 repeated that many times, beta 1. So what that corollary says is that P1 has to divide one of these factors. P1 divides Qi. Which one I don't know. Okay, since I have used I for this, let me just write J here. Qj for some j lying between 1 and m, that is any one factor among these will be divisible by P1. This implies since both P1 and Qj are positive integers after all, they are prime, that's fine, but they are positive integers and P1 is dividing Qj. So the size of Qj will be at least P1. Okay, it cannot be less than P1. It can be less than P1 only in one situation, if it was equal to 0. So if you are dividing some number by a positive integer, say P1, and that number which you are dividing by P1 happens to be less than P1, then division is possible, or rather divisibility is there only in the case that the number being divided is 0. Here, however, Qj is by definition, since it's a prime, it is a positive integer. So it has to be greater than or equal to P1. So this implies P1 is less than or equal to Qj. But you look at these inequalities, Q1, Q2, etc. Q1 is the largest of all the Qj's. So that means this is less than or equal to Q1. So we have obtained this fact that P1 is less than or equal to Q1. Similarly, beta 1 greater than 0 gives us, if we now argue similarly, starting with the fact that Q1 divides A. Why? Because beta 1 is greater than 0. And moving on similarly, we get ultimately the fact that Q1 is less than or equal to P1, what will happen here? Q1 divides the right hand side, so Q1 will divide the left hand side. So by the corollary to lemma 132, Q1 will divide at least one Pi, but among all the Pi's, P1 is the largest, so Q1 will be less than or equal to P1. Hence, from these two inequalities, P1 is less than or equal to Q1 and Q1 is less than or equal to P1, we have P1 is equal to Q1. Okay, now we claim that this makes us conclude alpha 1 is equal to beta 1. In the text, there is at this point we have been asked to prove this fact. And this part we will do separately. Okay. For now, we assume that whenever we have got P1 equal to Q1, alpha 1 also has to be equal to beta 1. Hence, from A equal to P1 to the power alpha 1 times P2 to the power alpha